Good morning, students. This video is going to deal about the mapping function of the cache memory, module number 4, the memory system. Let's see what actually the mapping function is. Mapping function determines how a memory blocks are placed in the cache. A simple processor example I'm going to define for you people. So a cache consisting of 128 blocks of 16 words each, then the total size of the cache is going to be 128 cross 16, and which is going to give 2048 words. A main memory is addressable by a 16-bit address. Then the main memory has a 64 kilo words, and the main memory has a 4 blocks of 16 words each. So there are 3 different types of mapping used for the purpose of cache memory, which are as a direct mapping, associative mapping, and set associative mapping. Let's see one by one in detail. Direct mapping. The simplest technique known as direct mapping, which maps each block of main memory into only one possible cache line. Or in direct mapping, assign each memory block to a specific line in the cache. If a line is previously taken up by a memory block, when a new block need to be loaded, the old block is going to be trashed. An address space is split into 2 parts, index field and a tag field. The cache is used to store the tag field, whereas the rest is stored in the main memory. So direct mapping performance is directly proportional to that of the hit rate. For the purpose of cache access, each main memory address can be viewed as containing or consisting of 3 fields. The least significant W bits identify a unique word or a byte within a block of main memory. In most contemporary machines, the address is at the byte level. So the remaining bits specify one of the 2 to the power of n blocks of the main memory. So the cache logic interprets these bits as tag bits and a line field of or bits. This later field identifies one of them, m is equal to the power of r lines of the cache. So in this example, if you're going to see about that, here the example has been shown over here. The block j of the main memory maps onto a block j modulo 128 of the cache. When the memory block 0 or 128 or 256 are loaded into the cache, the block is stored in the cache block. Similarly, a memory block 1 or memory block 129 or memory block 257 are stored in the cache block 1. The contention may arise when the cache is full. When one more or where more than one memory block is mapped onto a given cache position, the contention is going to be resolved by allowing the new block to override the currently resident block. Memory address determines the placement of block in the cache. Obviously, the memory address is divided into 3 fields. Already we have seen that one, which is going to be called as an lower order of 4 bits is going to be 4-bit field, and selects one of the 16 words in a block, and the 7-bit cache block field, which the 7-bit determines the cache position in which new block must be stored, and the 5-bit tag field, the 5-bit memory address of block is stored in the 5-bit tag bits associated with the cache location. As execution proceeds, a 5-bit tag field of the memory address is compared with tag bits associated with the cache location. If they match, then the desired word is in the block of the cache. Otherwise, the block containing required word must be first read from the memory, and then which is going to be loaded to the cache. Such a way it's going to do its operation. It's simple to implement but not very flexible. Next, we are going to see about associative mapping. In this type of mapping, the associative mapping is used to store the content and addresses of the memory word. Any block can go into any line of the cache. This means that the word ID but bits are used to identify which word in the block is needed, but the tag becomes all of the remaining bits. This enables the placement of any word at any place in the cache memory. It is considered to be a fastest and the most flexible form of mapping. So here, if you're going to see about that, the example shown over here. So the memory block can be placed into any block of cache block position. The 12 bits tag bit will identify a memory block when it is going to be resolved in the cache. The tag bit of an address received from processor are compared to the tag bits of each block of the cache. This comparison is going to be done to see if the desired block is going to be present or not. It gives a complete freedom in choosing the cache location. A new block that has to be brought into the cache has to be replaced when an existing block if the cache is going to be filled. The memory has to determine whether a given block is in the cache or not. So the system is going to be more flexible and uses a cache space efficiently, and the replacement algorithm can be used to replace an existing block in the cache when the cache is going to be filled. And it's a bit of costlier than the direct mapping cache because of the need of search all 128 patterns to be get determined whether your cache is going to be there in the whether your block is going to be there in the cache or not. For that purpose, the cost is going to be bit higher in the associative mapping. Let's see about the third one, set associative mapping. In the set associative mapping, this form of mapping is an enhanced form of direct mapping where the drawbacks of the direct mappings are eliminated, and the set associative addresses the problem of possible trashing in the direct mapping method. It does this by saying that instead of having exactly one line that a block can map into the cache, we will group a few lines together, creating a set. Then a block in the memory can be mapped to any one of the line of a specific set. This set associative mapping allows that each word that is present in the cache can have two or more words in the main memory for the same indexed address. The set associative mapping, cache mapping, combines the best of direct and associative cache mapping techniques. In this case, the cache consisting of a number of sets, each of which consisting of number of lines. So the relationships are going to be get present such a way the 6-bit field determines the 6-bit field determines the set of cache consisting the desired block. So it is the combination of direct and associative mapping. So the cache of the block of the caches are going to be grouped into sets. Then the mapping allows the block of main memory to reside in any block of the specified set. So here the tag bit, the 6-bit tag bit of the address is compared to the tag set of the two blocks of the set. This comparison is going to be done to check if the desired block is going to be present or not. Such a way it's going to do this operation. So the cache which contains one block per set is going to be called as direct mapping. A cache that has k blocks per set is going to be called as k-way or set associative cache. Each block contains a control bit called as a valid bit. This valid bit indicates whether the block contains a valid bit or not. The dirty bit indicates that whether the block has been modified during its cache residency. When a valid bit is going to be 0 when power is initially applied to the system, and whereas the valid bit is going to be 1 when the block is going to be get loaded from the main memory at first time. If the main memory block is updated by a source and if the block in the sources already exist in the cache, then the valid bit will become cleared to 0. If processor and DMA uses the same copy of data, then it is going to be, as already we have seen, that it's going to be a coherence problem. So the advantage if you're going to see about the set associative mapping, the contention problem of direct mapping is solved by having a few choices of block placements, and the hardware cost is going to be decreased by reducing the size of the associative search. Let's see about the replacement algorithm. What actually the replacement algorithm? In the direct mapping method, the position of each block is going to be predetermined and there is no need of replacement strategy. In the associative and set associative method, the block position is not predetermined. If the cache is full and if new blocks are brought into the cache, then the cache control must be decided which of the old block has to be get replaced. When a block is to be overwritten, the block with longest time with respect to being transferred or referred is overwritten. This is going to be called least recent used block. And the technique is going to be called as LRU algorithm. So the cache controller tracks the reference to all blocks with the help of the block counter. Such a way, this replacement algorithm is going to be useful to have a performance of LRU is going to be improved by randomness in the deciding which block is to be get overwritten. Example, if you're going to see that while considering a 4 blocks per set in a set associative cache, a 2-bit counter can be used for each block. When a hit occurs, the block counter is going to be 0. The counter which value is originally lower than the reference one are incremented by 1 and other remain unchanged. When a miss occurs and if the set is full, the block with the counter value 3 is removed. The new block is put into the place and it is going to be counter is going to be set to 0 and other block counters are incremented by 1. Such a way it's going to do its operation in the particular way of replacement algorithm. Okay, let us see about the next one is going to be called as the performance cache performance consideration. When the processor needs to read or write a location in the main memory, it first checks for a corresponding entry in the cache. If the processor finds that the memory location is in the cache, a cache hit has occurred and the data is going to be read from cache. If the processor does not find the memory location in the cache, a cache miss has occurred. For a cache miss, the cache allocates a new entry and copies in data from the main memory. Then the request is fulfilled from the content of the cache. The performance of cache memory is frequently measured in terms of the quantity called hit ratio. A 2 key parameter is going to be commercially uses over there is nothing but the performance and the cost. In other words, the best possible performance at low cost. A common measure of a success is going to be called the price performance ratio, which is going to be depends on the how fast the machine instructions are brought to the processor and how fast the machine instructions are going to be get executed. So to achieve this parallelism, interleaving is going to be get used. A parallelism means both the slow and fast units are going to be accessed in the same manner. Let's see about the next one called as interleaving.